Hello, my name's Luke and I'm here to educate you through providing evaluation into the efficacy of inspiratory muscle training for improving endurance and more particularly assessing the benefits for elite athletes and endurance performers. In this session we're going to look at different techniques of inspiratory muscle training. We're also going to look at previous research into inspiratory muscle training and the endurance benefits of this, and also look at the main benefits specifically for elite level performers. So what is inspiratory muscle training? Well, the clue is in the name. It's training either strength or endurance of the respiratory muscles, for example the intercostal muscles. And this isn't done in the conventional techniques that you might be accustomed to. It is in fact broken down into three main methods. The first is known as isocapnic hypernia, and in general this refers to maintaining a constant level of carbon dioxide in the blood through hyperventilation. It is mainly restricted in the labs due to expensive equipment and the fact that you have to monitor CO2 levels. However, a commercially available device called the Spirotiger, as shown on screen, can be purchased. The second method is known as flow restricted loading, and this is restricting the airflow rate that can be taken in and expired from the lungs through changing the diameter of a small hole on a device known as the P-flex. However, you have to be able to measure and monitor the maximum inspiratory pressure when using this device. I have an example of a pressure threshold loading device. It's known as a power breathe, and this targets the inspiratory muscles only, and you have to breathe against a certain adjustable device, as shown there. You have to release the air through a valve against a spring. You have to breathe at a certain pressure which you're required to do so. You're also required to prevent breaths through the nose. Here is a quick demonstration. So why take part in inspiratory muscle training? Well, recently, respiratory muscle endurance is more commonly recognised as a limiting factor for exercise, therefore affecting overall fatigue and endurance capacity. And this can be summarised through the belief of the respiratory muscle metaboreflex, a sympathetic response to respiratory muscle fatigue during high-intensity endurance work, first shown by Harms et al. In 1997. And this is summarised on the left-hand side of the diagram on screen now. The redistribution of oxygenated blood to the fatiguing respiratory muscles has a knock-on effect onto leg fatigue. Therefore, this results in increased competition for oxygen and nutrients from the blood, as well as increased RPE of both locomotor muscles and the breathing muscles. And as a result, this limits performance. Now to look at some previous research. One of the key breakthrough studies was done by Imbar et al. In 1999, and this hypothesised specific inspiratory muscle training would lead to improvements in respiratory muscle function and aerobic capacity. 20 track event trained participants were separated into two groups whilst continuing their regular training programs. 10 were put in the inspiratory muscle training group where they performed pressure threshold training for 30 minutes 6 times a week for 10 weeks. The control group, known as sham, also did the same training protocol, however they had no resistance on their pressure threshold loading device. The participants then took part in a treadmill exercise capacity test, an extra resistance endurance test to measure the endurance of the respiratory muscles, and also a strength test of the respiratory muscles, where they measured maximal inspiratory pressure. The results of this study show that increases in strength of pre versus post of 25% compared to the 0 in control. There was also endurance increases of around 10%, and there was also no difference in the control group. This increased endurance, however, was not associated with VO2 max, aerobic capacity, or arterial oxygen association. And this could be due to the maintenance of their own exercise program in the sham control group, as they are bound to see aerobic and endurance benefits apparent across a 10-week period regardless, as there was no significant difference between the groups. However, they could have solved this problem by measuring the rate of perceived exertion, as this would provide evidence of less pain or discomfort in the breathing muscles. This provided us with inconclusive evidence about the metaboreflex and its endurance capacities. Building on from this, Harms et al. 2000 conducted a study based around the effects of respiratory muscle work on exercise performance and cycling to exhaustion. 7 endurance-trained male cyclists completed randomised trials at 90% VO2 max. Respiratory muscle work was either increased via flow-resisted loading or decreased via a method called PAV or unchanged. The termination of each trial occurred when subjects failed to maintain over 50 rotations per minute on a cycling ergometer. Now the results show on this graph that with unloading respiratory muscles, subjects were able to exercise for on average 1.3 minutes longer than the control. And when loading the respiratory muscles, time to exhaustion decreased on average by 1 minute. Furthermore, RPE of locomotor muscles and breathing discomfort increased during muscle loading. Breathing discomfort is also known as dyspnea. Decreasing the work of breathing consistently led to significantly longer exercise tolerance across all 7 participants. Unloading the respiratory muscles during exercise was associated with reduced VO2, reduced hyperventilation, and reduced perceptions of respiratory and limb discomfort. Collectively, when performing a trial of high power output at 90% VO2 max, the results portray the metaboreflex theory and how this could be delayed as a result of inspiratory muscle training. However, elite performance is likely to last longer than 10.5 minutes and at a velocity of less than 90% VO2 max. So this has questionable reproducibility across the entire population of elite performers. Linked into harms, Leddy et al. 2007 conducted an exercise test to exhaustion also in experienced distance athletes, and this time they had 22 participants. These were split into 2 groups. 15 performed isocapnic hypnea and the other 7 were part of a sham control group. Inspiratory muscle group performed respiratory muscle training 30 minutes a day at 50% maximal voluntary ventilation, 5 days a week for 4 weeks. The sham group held their breath at total lung capacity. They then performed 2 tests, the first a treadmill running test to exhaustion, 80% VO2 max, and finally a 4-mile time trial running was completed pre and post intervention as fast as possible. The graph shows that the treadmill run to exhaustion in the respiratory muscle training group improved by 40 to 50%. And there were no changes in the sham control group, so this was not due to familiarisation of the test. There was a 4% decrease in the time trial length after inspiratory muscle training. And also, the average heart rate was higher after respiratory muscle training in the 4-mile time trial. Therefore, this suggests the runners were able to maintain a higher exercise intensity for longer periods, again suggesting that they were able to delay the sympathetic response of the metaboreflex. Pacing of the time trial will be determined by RPE, however this was not measured in the study, so we are unknown if it was effective in the perceived fatigue of the elite level performers. Another drawback of this study, as you can see on the graph, is that there was a wide variety in standard deviation. So this again suggests that this has got questionable reproducibility and reliability across the entire population. Could this be repeated again? Now, to answer whether respiratory muscle training is effective at improving endurance, it's important to take the stance of an athlete. All they want to know the answer to is, will it improve my performance? And in my eyes, the answer is yes. Despite several studies only reporting small improvements as a result of inspiratory muscle training, athletes are well aware the difference small improvements can make, particularly at elite level, and in most cases it can be the difference between first and last, which is why I've summarised this point. Small improvements make a huge difference. There is evidence that the metaboreflex can be delayed through respiratory muscle training, and I would strongly recommend this into a regular endurance training programme. Although several questions still remain about inspiratory muscle training and its effectiveness, there is no harm in adding it into training, as we have seen several time trial benefits in several different research articles. Finally, if you have any queries or would like to do any future research, please leave a comment in the section below and I will answer accordingly. Many thanks for watching.